Okay, in this video, let's continue the discussion about maximum modulus theorem, the third version. It's not blurred. Okay, the third version. Okay, so let G be a region in C and F an analytic function defined on G. Okay, G is the domain. Suppose that there is a constant M, capital M, such that the lim sup z approaching A ops value of f of z is less than or equal to M for all A in the extended boundary of G. Then ops value of f of z is less than or equal to M for all z in G. Okay, so in the third version, we try to control the modulus of f of z, but in the sense of lim sup for every point in the extended boundary. Remember, what is the visualization of extended boundary? If G is bounded for a bounded set, the extended boundary is the regular boundary. If G is unbounded, then the extended boundary is the original boundary, regular boundary union the infinity. Okay, so this is a visualization. Even though we call it extended, we just add infinity when we talk about unbounded region. Otherwise, extended boundary is a regular boundary. Okay. Okay, now let's see how do we prove it. We are not going to show directly ops value of f of z is less than or equal to M. We are going to show that the complement is empty. So how do we show the complement is empty? So let delta greater than 0 be arbitrary. So you find any bigger number, delta. Normally delta will be small, like 0.1, 0.001. And define H to be the set of Z in G such that absolute value of f of z is greater than M plus delta. You see, this is the opposite of the conclusion, so that's a complement. And we are going to show that such H is always empty for all delta greater than 0. For every delta greater than 0, this set is always empty. And then it is equivalent to say the statement is correct, the theorem is correct. There's no point z so that ops value is greater than M plus whatever small delta. Then it is equivalent to say all the modulus of f of z is less than or equal to M. Okay? So how do we show that? We have several steps. So first, because absolute value of f of z is continuous, f is analytic f is continuous, ops value function is continuous. So this is a continuous function, and this strict inequality give us H is open, because this is an open set. The preimage of open set is open set. Okay, so H is an open set. Second, we are going to study the lim sup condition. What is a lim sup? Lim sup of ops value of f of z, z approaching a. By the definition, let's see what is the definition. It's a limit r approaching 0 from right hand side, and then the supremum of absolute value of f of z, where z belong to G intersect the ball centered at A with radius r. Okay, so this is G. This part is G. This point is A. Then you pick up an open disk. And this is the point you're going to select for the evaluation of the supremum. Okay? Okay, then you compute this supremum that is denoted by the lim sup, and then you are going to shrink this r. This is r. You're going to shrink r to 0. So that's why we understand it as a behavior, or as the limit at A. And this one is less than or equal to m. Right? That's the definition of a lim sup. All right. Limit is less than or equal to m. Then we get there exists an r greater than 0 such that for z belong to G intersect ball AR, absolute value f of z is less than m plus delta. Because the lim supremum is going to be less than m plus delta. So inside this open set, this whole thing, all the elements with the ops value of f of z is going to be less than m plus delta. Okay, for every delta you can find an r. For every delta you can find such r with this property. Okay, so in this neighborhood, it's less than m plus delta. So it means G intersect the boundary. This whole set, this shadowed region, this set intersect H is empty. H, what is H? H is greater than, this is less than. So it means this H does not touch the boundary. So H intersect the extended boundary is empty, because A is a random point from the boundary. And also there's a gap. So this implies the closure of H is completely contained in G. The closure of the boundary completely contained in G. It always have a gap. Every point you can find such R. So you get that the closure of H is contained in G. Okay, and this condition, see, in this argument, this conclusion holds for bounded and unbounded. Bounded and unbounded G. So it doesn't matter what G you have, it is always correct. Okay, so if G is unbounded, G is unbounded, then there's a situation. The boundary point from the extended boundary could be infinity, and A is infinity. If this is a case, let's check what is the corresponding neighborhood. This is neighborhood. Is a corresponding, the corresponding neighborhood of infinity with a radius r is ball infinity. R is equal to the set of z such that ops value of z is greater than r. This is the neighborhood. It's outside of the closed disk. This is neighborhood for the infinity, outside the closed disk. And we know that H intersect G intersect this neighborhood here is empty. Is empty. So this implies H is totally contained in the ball centered at origin with radius r. So this is outside of the closed disk. Here is inside the closed disk because its intersection is empty, so it is totally contained in the inside the closed disk. Okay, so it's contained in this closed disk. H, the complement of H, sorry, not the complement. The closure of H is bounded. Closure of H is closed automatically, and now it is bounded. Then it implies closure of H is compact. This is exactly what we need. Okay, so when the closure of H is compact, you can use open disk to cover it, right? Remember that you can use open disk to cover it and the stuff. So the second version of the maximum modulus theorem applies. Whenever you have a compact set, then you can apply the second model. Because in the definition, in the proof of the part, we emphasize when G is bounded, the image of G is also bounded, right? Bounded and the closure is compact, then you can find the special point A. Okay, so let's see. We can apply the second version, the maximum modulus, and now we are going to get a contradiction, right? So for Z in the boundary of H, for Z in the boundary of H, if Z is in the boundary of H, then and f of Z is m plus delta. M plus delta. What is a H? H is here. It's greater than m plus delta. And the boundary condition will only happen if you're talking about the boundary of the image. Right? The boundary will only happen if you talk about the boundary of the image. But here, this condition contradicts to the second version, the maximum modulus for the H. Why it is contradicted? Over H, the maximum remember, over H, the maximum is definitely greater than m plus delta, because by definition it's like this. But on the boundary, the modulus, the maximum of upper value is exactly equal to it. They are not equal to each other by the second version. Of a maximum modulus theorem, MMT. By the second version, they should equal to each other, right? So here, when we apply the second version of modulus theorem, we apply it to H, to this set. If you have contradiction, it means you cannot apply the maximum modulus. Why you cannot? So you get the conclusion. This failed the MMT. The conclusion is that either H is empty or F is constant. Okay, either H is empty or F is a constant. Well, actually, H is empty, that's what we want. But if H is a constant, if H is empty, we are done. If F is constant, if F is a constant, H is still empty. Why? F is constant, then from the statement, lim sup is going to be a constant, strictly less than m, and then the upper value of f of z is going to be less than m for all z automatically, then H is still the empty set. So from either case, we can get H, the set H to be empty, right? From either case, H is always empty, then we are done. All right, so you can see that we use this extended boundary to study or to shrink, to control the growth rate of the modulus of analytic function at infinity. So this is important. We only discuss we only discuss a case when G is unbounded, because in that case you have the boundary infinity. If G is bounded, you don't have to go through those stuff. You directly apply the result of the second MMT, right? When G is bounded, H is also bounded. H is bounded, the closure of H is bounded. You can also apply the second version, the maximum modulus there. You apply it here, you still get either H is empty or F is constant. So that's why you see in the whole in the main part of the computation, we always only concern the case when G is unbounded, because in this case you have infinity. That is a case the second version of MMT does not cover, because in that case we have no idea why H bar is compact, is bounded. Okay, when you have a compact domain, then its image, continuous image, is also compact. When you have a compact set, you can draw the circle and choose an A so that A is a maximum. Remember that. If you don't remember, go back to check the proof and see how we construct, find the boundary point on the image. Okay, so this is the proof of the third version of a maximum modulus theorem, MMT. So we only want to control the infinity. Okay, and let's back to the example we discussed. Remember last time we had that example. In the example, we had that the domain G to be Z in C such that the imaginary part of Z is less than 1/2 pi. Imaginary part, upside of imaginary part. It's a horizontal band. It's a 1/2 pi I and a negative 1/2 pi I. And we can see that the analytic function is exponential by e to z. And For this function, the lim sup of ops value of f of z is less than or equal to 1 when z approaches a, but a belongs to the boundary of G. While when a is infinity, the lim sup is not bounded by 1. It is infinite. So there's no m. How do you get this infinite? You choose this z along the real axis. When it is along the real axis, it will blow up. So again, this example cannot be covered by the third version of MMT, maximum modulus theorem. Okay? Okay, so the exercise for this part, it's on page 129. You can try problem 1, problem 2, and problem 7, and problem 8. Okay, so if you have a question, we can discuss it. Okay, so we finished the first section, the section of MMT in the chapter MMT. Section maximum modular theorem in the chapter the maximum modular theorem. Okay, now let's check the second version. Not second version, second section. Schwarz theorem, lemma. Schwarz lemma. Schwarz lemma. Let's see the statement of a Schwarz lemma. What is a Schwarz lemma? Let D be the open disk, unit open disk, and suppose F is analytic on D with two given conditions. One, ops value of f of z is less than or equal to 1 for z in D. Okay, for z in D. So this means f will map D to D. It maps the disk to the disk into the disk. And second, f of 0 is 0. It's like the normalization condition. F of 0 can be mapped to any place, but we assume it is normalized. It just maps 0 to 0. Okay? The first condition means f is from D to D. Second condition means f is normalized. Okay. D to D normalized. And then let's see the conclusion. Then we have ops value of f prime of 0 is less than or equal to 1. So we can control the ops value of the derivative, ops value of the rate of the change. And we also know that f of z ops value is less than or equal to z for all z in D. Okay, so you control the derivative at 0, and also you control the modulus of the image by the modulus of z. Okay, so that's an inequality. And moreover, if we want, there's some stronger conclusion. Moreover, if this is inequality, if you have equality, ops value of f prime of 0 is 1, or if ops value of f of z is equal to ops value of z for some z not equal to 0. If this equality holds for some point not equal to 0, because f0 is equal to 0, this is trivial, this excluded. Then any equality holds, then there is a constant C with ops value of C equal to 1 such that Fw is C times W for W in D. So if any one of equality holds, then this is just a rotation. It's just a rotation function. You multiply by C, you kind of rotate this Z. You just change the argument, right? C times W is a rotation. So that's a very, very strong result. Any one equality holds, you have to have a rotation. All right. Now let's see the proof. The proof is not extremely difficult, but it's very creative. So first we define a function g from D to C by g of z is equal to f of z over z. You have the division, so the denominator is not equal to 0. Then what happens if z equal to 0? We define g of 0 is equal to f prime of 0. Okay, then this is at least it's a continuous function, right? When z approaches 0, g0 is equal to the derivative. So that's at least it's continuous function. And you can show that g is analytic. To show the analyticity, first, this expression is is differentiable at any z not equal to 0. So what you need to show is that you need to show g prime of 0 exists. You just try by the definition of a derivative. You can show g is differentiable. And we also know that a function is differentiable, then the function is analytic in a complex plane. Analytic means continuous differentiability. But we already showed that the differentiability is equivalent to the analyticity. So you only need to show g prime of 0 exists. That's everything you need to do. Try it. Okay? So you have analytic function. Now let's assume you have analytic function. Then we're going to apply the maximum modulus theorem. This disk is a bounded set, so you only need to the second version of maximum modulus theorem. By the maximum modulus theorem for the disk 0R, close the disk 0R, the G, it is Z, yeah, it's a Z. And remember, Z is at most R. Z is at most R. F is at most 1. F maps D to D, so f of z has modulus at most 1. And they reach the maximum modulus on the boundary. On the boundary, z has modulus 1. R. On the boundary, z has modulus R. We are talking about this open disk. Smaller open disk. So that's why ops value of g of z is less than or equal to 1 over R. Okay, so this quantity, you get this quantity on the boundary of the closed disk. On the boundary of closed disk. And for every R, you have this condition. Let R approaching 1, we have that g of z is less than or equal to 1. Right? For all z in D. For all z in D, right? So you choose R approaching 1, this limit becomes 1, so ops value of z will be less than 1. Less than 1, okay, then let's go back to the situation. G is here. So f of z over z is less than or equal to 1 for z is not equal to 0, and f prime of 0 ops value is less than or equal to 1 because of g of 0, and this implies f of z is less than or equal to the modulus of z for z is not equal to 0. When z is equal to 0, this is 0 less than or equal to 0. It does not violate, so you can drop this case. So when z is 0, so you have equality, so they are unified. And here is the second case. So that's exactly the statement we want. So you only apply the maximum modulus theorem to the function g, you can automatically get it. But in order to apply the maximum modular theorem, you have to show g is analytic. So you need to do the division, the computation of a derivative at 0 for g. All right. Okay, so we're not done for the proof of Schwarz lemma. We only prove the general result. We still don't prove the moreover part. So moreover, if ops value of f of z is equal to the ops value of z for some z in D, inside D, and z is not equal to 0, or f prime of 0 is equal to 1, then this means g achieve the maximum modulus inside D, right? Because you see, inside D, oh, this is 0, this is g of 0. Then we apply the maximum modulus theorem. If you achieve the maximum modulus inside the region, then g of z is a constant c for some constant c with what? This c cannot be random. The ops value of c has to be 1. Ops value of c has to be 1. Why the ops value of c is equal to 1? Why this is equal to 1? Because you see, if it achieves the maximum modulus, g of z is equal to 1. G of z is a c, so c is equal to 1, right? Okay, so that's the reason c is ops value of c equal to 1. And this g of z is equal to c, then g of z is this, then so f of z is equal to c times z, and that's a rotation. And we completed the whole proof of the Schwarz lemma. So the Schwarz lemma technically is a direct application of the maximum modulus theorem, second version, to the special function g. All right, so to the special function g. So it's a very creative. It's a very clever proof. If you do not construct a G like this, possibly you can go through some complex steps, but you will get the same result. But still, but this is the most neat proof for the Schwarz lemma, right? Okay, so after we have the Schwarz lemma, we are going to use it to classify some conformal maps. So conformal maps. So Schwarz lemma is applied over the unit open disk D. So let's study a class of such analytic functions. So still D is open disk. For any A inside D, A inside D, upper value of A is less than 1. We define the Mobius transformation. The Mobius transformation depending on A, so we call it phi of A, phi sub A of Z equal to Z minus A over 1 minus A bar Z. Z minus A over 1 minus A bar Z. All right. Mobius transformation is analytic except the denominator is 0. If you want denominator equal to 0, you will get Z equal to 1 over A bar. Z is equal to 1 over A bar, or 1 over A complex conjugate. And 1 over A complex conjugate has modulus greater than 1, right? A has modulus less than 1. You flip it, its modulus is greater than 1. And so when Z is equal to this, the Mobius transformation is undefined. So it implies phi A of Z is analytic on D because this point does not belong to D. Okay, it's analytic on D. Another thing, we're going to show that we can see that phi A maps D to D. Why it maps D to D? There are two ways to show it. One way, first of all, we know it's analytic. One way, we apply the maximum modulus. We try to find the modulus along the boundary. So phi A of e to I theta. Okay, it's a e to I theta minus A over 1 minus A bar e to I theta. And we factor out e to I theta from the denominator. Remember, when you factor out e to I theta has norm 1, upper value 1, so you still have this. You don't see the e to I theta. We just factor out this factor outside, and it has, this is 1. And the complex conjugate and the original number, complex number, they share the same modulus, so this is 1. Okay, so when the modulus of the analytic function on the boundary is equal to 1, then by the maximum modulus theorem, phi A of Z, phi A of Z has modulus less than or equal to 1. So it maps D to D. It maps D to D. Okay? this is the application of the maximum modulus theorem. And if we don't use this theorem, we can have another way to prove it. So how do we prove it? We just do the direct computation. Let's see how do we do the direct computation. We want to show this expression has modulus less than 1. This is idea, that like the idea. It's not a proof, it's idea. We want to show this is less than 1. Okay, so ops value is hard to compute, but if we square it, we square the left side, we square the right side, it's still 1. Okay, so square of the modulus is z times z bar, right? This one is easy to compute. This one is ops value of z squared is hard to compute. So that's why we need this. Okay, so in order to show it is less than 1, it suffices to show this one. Remember, we're talking about idea, the analysis. It's not the proof. Later, we will go backward. And then you do the computation. The complex conjugation can be applied to every term. So you will get a z minus a, z bar minus a bar, and here's 1 minus a bar z, 1 minus a z bar, less than 1. We need to check this. Remember, we are going to backward this way. Okay, let's continue. This one is just plain computation. And now you compute the numerator, z bar minus za bar minus az bar plus aa bar. This is numerator. 1 minus az bar minus a bar z plus aa bar zz bar less than 1. Remember, we're going to go backward, and let's collect them. So this is zz bar, aa bar. It's a z bar square, ops value square minus za bar, az bar. It's twice of the real part of az bar. They are complex conjugate to each other. You add them together, you only get the real part. It's a real number. The denominator is the same thing, 1 plus, this is a ops value of a bar, ops value of z bar, minus twice of az bar less than 1. Remember, we're going to go backward. And then you need to know that this is a positive number. This is a positive number. How do you know it is a positive number? 1 plus it's a the Cauchy-Riemann equation inequality, right? Cauchy-Riemann inequality. Cauchy inequality, no Riemann. Cauchy inequality. A squared plus b squared is greater than or equal to 2ab. And this one is greater than 2 times the real part of az bar. Yeah, right? You just check it. Okay, so this is so once you move it to the left side, it's a positive. When you get a positive stuff, you multiply this inequality by this a positive number, you still have the same thing. Okay, so you just multiply this inequality by the denominator. Remember, we're going to go backward. And then those two terms are identical. You cancel them, so you will get this. And then you move everything to the right side. What is this? It's a simple factorization. It's a simple factorization. This one is greater than 0 for sure because Z is inside the open disk, unit open disk. A is also inside the open unit open disk. So those two subtractions are both positive, products positive, and then you start from here, go backwards step by step, you will eventually have this, right? So this proof is a plain computation. It does not depend on the maximum modulus theorem. It never depend on that. So maximum modulus theorem can give you a very quick result, but you have to know it. And this you can just compute and compute and compute. Okay? So anyway, either works. We show that the phi A maps D to D, this one. Phi A maps D to D. Next, we're going to show, for every A, it will map the D to D. And let's check the other relation. What is a phi A composed with phi negative A of Z? Okay. Phi negative A of Z, let's check what it is. Here is a phi A. So phi negative A, so it's a Z minus negative A, Z minus negative A bar, Z, right? And this becomes phi A of Z plus A, Z plus A bar Z. And then you apply phi A here. It's just very, very long computation. Whenever you see Z, you use this one. So Z plus A over 1 plus Z bar A minus A over 1 minus A bar Z plus A over 1 plus A bar Z. It's not very bad. So you multiply top and bottom by the denominator. You get Z plus A minus A times 1 plus A bar Z. It's 1 plus A bar Z minus A bar Z plus A. Assume my computation is correct. I hope I don't make a mistake. Okay, and let's continue the simplification. We will have a Z plus A minus A bar Z times A. So A times 1, A times A bar Z. Here, so 1 plus A bar Z minus A bar Z minus A bar. So cancel them. You have Z minus A bar Z over 1 minus A bar. Effect out the Z, you see that the coefficient is cancelled. So what we get is phi A phi inverse negative A of Z is equal to Z. Okay, that's just computation. I want to show the computation if you can do that. Okay, then this implies phi A maps D to D is 1 to 1. Is 1 to 1 and onto. Right? For every Z there is a preimage. So it's onto. And from here you know it is also 1 to 1. And similarly, so this is a very, very nice conformal map or Mobius transformation. And we also showed by the computation that it maps the boundary to the boundary. It also maps the boundary to the boundary. So to summarize what we have, we get the following property. The proposition if the ops value of A is less than 1, then phi A is a 1-to-1 map of D, which is an open disk, onto itself. Okay, the inverse of phi A is phi negative A. Furthermore, phi A maps the boundary of D onto the boundary of D. Phi A of A is equal to 0. This is just a direct examination from the definition. And phi A prime of 0 is 1 minus ops value of A squared. And phi A prime of A is equal to 1 minus ops value of A squared to the power negative 1, the reciprocal. Okay, so those computation, just do it by yourself from the definition of the function. So you will get those 3 conditions. And these stuffs we just showed. I didn't compute this one, but I showed that. Okay, so this is like the summary of the this type of a Mobius transformation. Okay, so in the next video, we will see how we use this proposition to classify the one-to-one analytic functions from D to D, from D onto D, right? So we are going to see the application of this simple observation or simple computation in the next video. Okay, we'll stop it here and we will start another video. Thank you.